So hello everyone. First of all, it's great to be here, and thank you, Paulo and John, for inviting me. It's a great pleasure and honor for me. As you can see, I'm from the Department of Aerospace Engineering. You might think, what am I doing here? And so I promise you that this realization will take it to the extreme because we're engineers. And so I'm going to talk a little bit about a work which started a couple of years ago when I was a postdoc in the Applied Mathematics Lab with John Bush. And this is an attempt to realize a hydrodynamic-inspired relativistic pilot wave theory. And so, first of all, I would like to thank Mark Fleury for the generous financial support during my postdoc period at MIT. I honestly think that without his support, which was critical in critical times for me and for the whole project, I wouldn't be here presenting it to you. So thank you, Mark. And also I want to thank John for our past and ongoing work on this super interesting work for me. I also want to thank the Israeli Science Foundation, the ISF, for supporting our work on stability of multiphase flows and the Center for Security Science and Technology. Both are helping us in this project as well. And I want to thank a special thank to Sonny White from the Limitless Space Institute, and my dear friend and colleague Charles Chase from UNLAB, who I'm working with on I would say super high-risk project that I wouldn't be able to work on without the support. And what we're trying to do here is in this with this LSI project is to think about ways where we can exploit some notions from the hydrodynamic analog and quantum mechanics to engineer a device for a future propulsion system, especially propellantless propulsion. And so thank you for your support. And so I also want to show you a little bit where we're talking from. So we're talking from the Technion in Haifa, Israel, which you can see here. John showed us yesterday a star, the stars all over the world. And unfortunately, the star that John picked just covered all over the area of Israel. So I had to show you how it looks like beneath the star. So we're here. We're from the Aerospace Engineering Department, and I'm very lucky to have a wonderful group of people working with me, graduate students and research scientists. And here, what we do is we combine theory, high fidelity computations, and experiments to reveal some fundamental principles, theoretically, of different flows that may involve reactions, but also interactions with particles. And that's how we can connect somehow the hydrodynamic analog and our mainstream work. So for this talk, I'm going to briefly go over my outline here. So I'm going to talk about a little bit about the hydrodynamic analog and de Broglie's theory, from which the hydrodynamic quantum field theory stems. And this this new theory is what I've been working on for the last 3 years with John Bush. I will show you the steady motion, free particle solutions, and force particle. Basically, this is theoretical work, but it's a very numerical work as well. So we use high fidelity simulations now to be able to extract some features of this new theory. And finally, if I have some time, I would very much like to show you our very new results that we have on a non-relativistic, fully classical interpretation that we are attempting to solve. And I think we already have some interesting results. So I want to begin with de Broglie's theory, and you all know that in 1924, de Broglie introduced the idea that a particle has associated with it an intrinsic internal clock. And Anna Maria yesterday in a wonderful talk talked about this synchronization of clocks and the particle resonating with its own wave field, or the Zitterbewegung and zero-point field. And maybe the simplest manifestation of this idea is here. So for particles at rest, we have E naught equals mc squared. And the Einstein-de Broglie relation connects it to the h bar omega c, where omega c is the constant frequency. And then when the particle is set in motion, we can write the same equation, but now boosted with the Lorentz boost factor gamma, and we have this relation. Now, together with the famous momentum relation of de Broglie, we can write the relativistic energy equation, which we all know. And now, quantizing this field and writing it as a field, you can immediately see that we can write the Klein-Gordon equation, which is a relevant relativistic particle field equation, from which its dispersion relation can be extracted. So you can imagine, you just take the energy squared and divide it by h bar omega. And then we have this, okay? So first of all, when we look at the Klein-Gordon equation, we can see that it's, we can think about this equation as a coupled resonator equation, where the Compton frequency is its natural frequency. And we can see it also here. So and this is the dispersion relation of Klein-Gordon, where omega is the frequency. Here we have the rest mass energy divided by h, which is Compton frequency. And then we have this term, which is c squared k squared. Now, for particle at rest, of course, this term is gone, and we're left with the Compton frequency. And now comes the analogy. So what we've been looking at is water waves. And if we write the dispersion relation for water waves, we see something like that. So for deep gravity capillary water waves, this is the dispersion relation. And at first glance, you can definitely say, okay, this is certainly not the same dispersion relation, right? We have a cubic term here for k, for the wave number. And here we have k squared. But if we think about the Faraday wave at resonance, then this dispersion relation becomes, and the waves become essentially monochromatic. And de Broglie was also talking in his later papers, I think it was 1970, he talked about quasi-monochromatic waves as well. We will touch on this point a little bit later. But this is key. And if we think about the Compton frequency as the natural frequency of matter waves, we can also think about GK as the natural frequency of Faraday waves. And if we just think, so the square root actually of GK is the frequency. And if you think about square root of GK or G over lambda, this gives us the natural frequency of a simple pendulum due to gravity. So this is one part of this rationalization that we can compare to the matter waves. The other part of this, so sigma k over rho in capillary waves is actually the signaling speed, or the highest speed in our system. So this is C square, so this is a speed squared. So we can relate this sigma k over rho to the speed of light squared. So if we can do this analogy, we have a framework in which we can compare relativistic matter waves to water waves. Now, De Broglie suggested that a particle may exchange rest mass energy with wave energy, but he did not specify a wave form. Neither did he specify the mechanism for generation of the wave. And this is exactly what we try to do here. Another interesting thing, I'll just go fast over this relation. So if we take the Klein-Gordon equation and strobe it, or modulate it by this by the Compton frequency, we can actually write a modified Schrödinger equation just by replacing the variables at the Compton frequency here. And writing it here, you can see that we have the Schrödinger equation, basically a non-relativistic term of the equation is here, whereas here we have the relativistic term, which is usually neglected for non-relativistic speeds. So it's very interesting for us now to think about the Klein-Gordon equation. How would an oscillating disturbance affect the generation of waves? In other words, what would happen if we put a source term here? Now, this notion is not new, and I had to put this this quote by Holland again that you saw yesterday, and John read it to you, but it's exactly what. So the premise of this quote is exactly what we're going to do. So Holland suggested that we may use a source term in the pilot wave field through a inhomogeneous term in the wave equation. That's exactly what we do. I want to mention other recent pilot wave models of quantum dynamics, which are inspired by the working droplet system. So we have Borghese. It's a beautiful work using elastic beads, and the work by Drizet. Both were using the Klein-Gordon equation in classical analog. And then we have a recent paper by Schinbrot, who used multiple particles and the dynamic pilot wave and bound for the dynamic pilot wave bound states. But what we're doing here is this. So basically, we take our field equation, the Klein-Gordon equation, and perturb it. So we have a disturbance here, localized at the particle location xp, and this disturbance is oscillating at twice the Compton frequency. Now, notably, this is exactly the Schrödinger's Zitterbewegung frequency. And as you can see here, if this is an oscillator, we use the twice the Compton frequency, we excite this parametrically at twice its natural frequency. And it has been shown that this is optimal excitation of this field. And we use this equation for the waves. For the particle, we use a dynamic equation that looks like this. So on the left, you can imagine that we have a momentum term, gamma mv, that you can see here, which is a relativistic momentum. The mass is absorbed in this alpha, which is a coupling constant to a wave gradient driving force, just as in the hydrodynamic system. Now, by using this, we can show first to start off by just prescribing the motion of a particle and see what we have in terms of waveform. So we have an oscillating particle here in black that creates waves. Okay, and we can see the waves here in color coded. This is a spatial temporal map. So this is space normalized by the constant wavelength, and this is time normalized by the constant period. And here we can see a snapshot around this point in time. We can see the dispersion of waves. Now, what happens when we move the particle? So here we have a particle moving at constant speed. We are prescribing the particle, so we have no dynamic equation here. So particle moves at 0.7 c in this region. And we can notice some interesting results. For example, if we measure the wavelength here, for example, close to the particle, and put it back in our relativistic momentum equation, we can extract in yellow the velocity back to the velocity, and we can see that it correlates very well with the velocity that we prescribed. This was very interesting for us to see, and here you can see different snapshots of the waves. Interestingly, so here you can see in solid lines a snapshot for the particle and the wave, and in dashed line you can see the same waveform strobed at different periods. So we can see that the particle is gliding along with the wave, which is very similar to what we have in the hydrodynamic case. Also interesting to see in different velocities. So we have beta 0.1, beta 0.2, and 0.3, and we can see that essentially we have two wavelengths characterizing this the propagation of a wave field. And as you can see in the inserts, the bars, we can see that they correlate to the de Broglie wavelength, and the fast oscillation correlate to the competence. So this is a two wavelength system. And finally, we can let the particle move freely. So here we do not prescribe the motion. We let the particle move according to the wave field and driven by the gradient of the waves. And here, again, this is a spatial temporal map where we have the particle here oscillating. We just initially, we perturbed the particle very in a very small amplitude. So it is not starting as in a symmetric case, but very small perturbation. And what we can see here is that the particle creates standing waves. So in the inset here, you can see the particle seems like it's not moving. It's actually moving very. So we have wobbling in a length scale much smaller than the competence. But eventually, symmetry is broken, and we can see this region here is actually a chaotic region. If you run many simulations, we'll see the particle going in many different trajectories. But eventually, we will see that the particle locks into a quasi-steady motion. Now, again, if we measure the wavelength close to the particle, we still get P equals h bar k, right? So I think we can safely say that we have a classical interpretation in which the particle is driven, as in the hydrodynamic case, by gradients of the field in a non-relativistic manner. But we still get the quantum statistics right, for the free particle. Now, remember that we talked about the strobing. So if we take if we take a part of this, the same simulation, and strobe it, we see something very peculiar. It's kind of hard to see it here, but this is the particle strobe. We see only those strobe particle locations, but through the wave field, we can actually see the traces of the particle reminiscent of earlier, or this is memory that we see here, right? So I don't know if you can see those dots, white dots. This is the particle, but it's not real particle. This is the particle that we're moving. These are actually phantom particles. So we have a signature riding along with the particle, basically dressing the particle as in our hydrodynamic case. But we can see it only in the strobe framework. And finally, here we take the spectrum, the spatial spectrum of our particle motion, not the waves, it's the particle motion. And here in the inset, we can see the velocity of the particle as a function of space, and you can definitely see the signature, different signature of the velocity modulation. But very interesting to see is that when we take this spectrum of the velocity modulation, we get this peak in exactly the Broy's wavelength. Now, this was very interesting for us to see. It really looks turbulent. It's not turbulence, but the spectrum looks turbulent. As a turbulent analogy, we can see some coherent structures coming about from these interactions, this nonlinear interaction. When you look at the temporal FFT now, we can see that we drive the particle at twice the quantum frequency, but look what we get. We get excitation of the particle motion at a modulated frequency, which is essentially plus minus Kc. If you remember, so the velocity modulation is at the Broglie wavelength corresponding to P equals h bar k, whereas the temporal frequency of the modulation is Kc, which is exactly what you would expect from Einstein's energy equation. I think I don't have much time, so I'll just jump a little bit further. I want to show you our recent work on a non-relativistic classical interpretation and this work has been fully conducted by my graduate student, Idan Shausho, who is wonderful in both the interpretations and conducting this research. And what we have here is the same Klein-Gordon equation disturbed or perturbed by localized oscillations. This is a Gaussian here, but here, as you notice, we don't use the relativistic dynamic equation. Instead, we take a fully classical Newtonian equation. And what's super interesting about this problem is that what we get is fast superluminal oscillations, which is not surprising, as we do not have the restriction of relativistic dynamics, but we can safely say that all the oscillations that we get are at the Compton scale. Inline oscillations are comparable to the de Broglie wavelength again. And so the bottom line is that the strobe, if we take the same solution and strobe it, the strobe particle do not exceed the speed of light in any case. And no matter what alpha, the coupling constant, we take, we do not exceed the speed of light. And this is because of the interaction of waves and the particle. So I hope I didn't take much of your time. The last slide I want to show you here is some comparison between the pilot wave hydrodynamics and our new theory, the HQFT. So the driving force in the hydrodynamic analog is the backward vibration, whereas in HQFT it's the Zitterbewegung at twice the Compton frequency. It is exactly twice the Faraday frequency in our HQA. And so the wave natural frequency, as we saw, is the square root of KFG, and whereas in matter waves is the Compton frequency. The pilot wavelength is the lambda f. It's a monochromatic lambda f, whereas in our case we see both lambda c and lambda b, the de Broglie wavelength and the Comptons. This is a special relation, and the wave energetics is very interesting. So we exchange gravitational potential energy with surface energy in the hydrodynamic case, whereas in HQFT we exchange rest mass energy with field energy. And so we can correlate our surface tension in the hydrodynamic case to h bar, and this is basically our new analog. So I think I'm almost finished. I want to conclude that we have a new model of quantum dynamics, which is based on the conceptions of de Broglie, but informed by the hydrodynamic pilot wave system, which explicitly treats the coupling between the particle and the wave. And we see that both kinematic and dynamic simulation exhibit the emergence of quantum-like statistics, which are a reflection of the particle velocity modulations, as we can see also in our not so clean, I shall say, simulations. And for ongoing work, we're working now, I'm working now with John on force particle simulations. So up until now, we talked about the prescribed motion and the free particle. And now we're working on the simple harmonic oscillator potential. And we already have some interesting features coming up of this realization. And finally, as I show you just a little bit, we have a new classical, fully classical, non-relativistic interpretation of the free particle, which reveals both relativistic quantum statistics, although we do not take any relativistic measures here in our dynamic equation. Thank you.